Yeah, I don't know what Kent would think about that. So question 17 is pretty straightforward, actually. It should remind you of the KW calculation we did in class on Thursday, because we've got this equilibrium constant, right? We've got ammonium sulfide, breaks down to give you ammonia and hydrogen sulfide. And it tells you that the Kc, the equilibrium constant, is 1.26 e to the negative 2. What's the concentration of ammonium? So my equilibrium expression first is where I would start. My equilibrium expression is going to equal the concentration of ammonia times the concentration of hydrogen sulfide, because this is a solid. So we can ignore that from the equilibrium. And that made our calculation a lot easier. So I don't know the concentration of ammonium. I don't know the concentration of hydrogen sulfide. They should be the same because their coefficients are the same, both 1. So I can say they're both x. I can call them both x. And now I've got an equation I can solve. I can say 1.26 e to the negative 2 equals x times x. So 1.26 e to the negative 2 equals x squared. Take the square root of both sides, and x equals 0.112? Don't have it right in front of me. Yeah, 0.112. Right, and that's going to be our concentration of ammonia in this reaction. We could do that in this case because ammonia, hydrogen sulfide, 1-to-1 ratio. We don't know either of them, but we can set them both equal to x because their coefficients are equal to each other. Exactly, Titus, right? We can call them both x because their concentration should be equal. For every mole of ammonia we make, we're going to make a mole of hydrogen sulfide. So we can call them both x and get an equation we can solve. All right, equilibrium constant for the gas phase reaction outlined below is 4.34 e to the negative 3, right? At equilibrium, what does that tell you, right? What does that tell you for this reaction? K is much, much less than 1. So what can we say about this reaction with an equilibrium constant of 0.00434? All right, I'll answer this one, then we'll jump in back to that one. Right, when K is much less than 1, we calculate equilibrium constant as the concentration of products over the concentration of reactants. So when K is much less than 1, right, that's a reaction that favors the reactants. Equilibrium falls on the left. So we would say reactants predominate in that reaction because we've got a small value of K. And to go back to the previous question on 17, so if it was 2 moles to 1 mole, well, not exactly, right? It wouldn't be x squared and x, because would that be the relationship, right? What's the relationship between 2 and 1? It would be 2x and x if the coefficients were not the same. Does that make sense? Why it would be 2x and x? All right, if I had this reaction, if I had, AB2 breaks down into A and 2B, and I didn't know the concentration of A, I didn't know the concentration of B, I would set it up in terms of x, where this would be A, or A would be x. For every 1 mole of A I'm going to make twice as much B, so B would be 2x. And then to set it up in my equilibrium expression, let's say this is a solid to make our life easier, right? Then setting it up in my equilibrium expression, I'd have the concentration of x times the concentration of 2x squared. So it still gets squared, but it gets squared in the equilibrium expression, not when we're comparing the 2 unknowns. And you won't see anything like that on this exam, but when we get into solubility, you'll see examples like that. So You don't need to worry about that for Tuesday, but definitely going forward, you will see problems like that. And then question 19, let's see. Is there anything different when there is also a reactant with an unknown concentration? We're not going to see that, because then you would have a problem you can't solve, right? If I don't know a reactant concentration and a product concentration, then we're going to be stuck in a situation where we can't find equilibrium concentrations for all of those, because we need to know at least initial concentrations of our reactants. If we don't know our initial concentrations of reactants and our equilibrium concentrations of products, then there's no way to solve that problem. So you would at least have to know initial concentrations of all your reactants. Question 19, I think I'm missing the top half of question 19. I hate when that happens. Question 19, equilibrium constant for the gas phase reaction is this: if the system has 1.02 moles of nitrogen, 1.97 of hydrogen, 1.93 of ammonia, what direction will the reaction move to reach equilibrium? All right. So question 19, right, is Q a reaction quotient? We calculate Q the same way we calculate K. So Q for this reaction is going to be the concentration of ammonia squared all over the concentration of nitrogen times the concentration of hydrogen cubed. We'll plug in the concentrations we have. So Q equals 1.93 squared over 1.02 times 1.97 cubed. Multiply all those together and I get Q equals 0.477. And they told us at the start that the equilibrium constant is 4.34 e to the negative 3. So in this case, right, Q is greater than K. So that means we've gone beyond equilibrium. So to return to equilibrium, the reaction has to move to the left. The reaction has to make more reactants. Because Q is greater than K, we've gone beyond equilibrium. So the reaction will move to the left. We can cross out that, we can cross out that, we can cross out that. The reaction will move to the left, forming more reactants, right? As we move to the left, we're actually going to consume products. So it can't be choice B. So that ends our next video segment.